I'll fold it.
So no questions? You guys are good? Ooh, there was a. Oh, I have a comment on the homework. Does anybody have the text? No. Okay. So this is a small comment on 8.1 homework. There are some problems. It's like problems. I think it's like the beginning problems. Or maybe not the very, very beginning, but there are some problems that say, for example, find the arc length. Let's say find the arc length of, I don't know, 1 over x on the, I have no idea if this is an actual problem, but I can't do from 0. Okay, 6 to 9, let's say. Using a numerical integration technique. So let's say it says S8. So what does that represent? What numerical integration technique is that? Simpson's rule with 8. So this number right here is the number of subsections. So I wrote on your homework assignment to use your program to do it for you. So you don't have to write out the whole thing. All you have to do is just put in the what's the function that ends up in the integral and use the program that you already made and have it do it based on the number of steps that you want to use. So the only thing to keep in mind, though, is that in your program, remember, n represents the number of points that you evaluate at, which is one more than the number of subsections, right? So if it says, for example, S8, then in your program, the way you guys wrote it, you would set n equal to 9. So that way you would have 8 subsections. So I just mentioned it because you would get confused. So you should get exactly the same answer as it's in the as what it says in the back of the book using your program. Yes? Does that make sense? So you change n to 1 more than the number of subsections, yeah. So that's it. Just a little comment. Yeah. Okay. So let's see. All right. So let's do some more Taylor polynomial stuff. So let's recall what we did last time. You guys remember what we did last time? We said that the Taylor polynomial, we call it Tn of x, which the video is online, by the way. But anyways, from yesterday. The Taylor polynomial of f of x centered at x equals to a is Tn of x is equal to the value of the function at a plus f prime at a times x minus a plus f double prime at a times x minus a squared over 2, right? Plus dot 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 f the nth derivative at a times x minus a to the n over n factorial. Yes? So this is what we derived last time, right? Yesterday? You guys remember this? It was only yesterday. So, okay. So if I write this in sum notation, this is equal to the sum, k equals to 0 to n of the nth derivative at a over n factorial times x minus a. Oh, whoopsie. These aren't n's. These are, what should those be? K. K, x minus a to the k. Okay. So this is the Taylor polynomial. This describes the Taylor polynomial of f of x of degree what? Degree n, right? Okay, so so we did an example last time. We did sine, right? So I want to do a couple more just to make sure that we're sort of comfortable with the idea. And what was the whole point of this? Like, why do we want to? Why are they useful, Taylor polynomials? What are they helpful for? You guys remember? Talked about it last time.
Approximating.
Yep, they're useful for approximating functions, right? By using functions that potentially could be complicated, you can approximate them with a simple function, which is a Taylor polynomial. And polynomials are very nice. You know, we can do a lot of things with polynomials. So, okay, so let's do an example. Let's say we want to find the general Taylor polynomial for f of x equals to 1 over 1 minus x, centered at x equals to 0. Okay, so let's see. All right, so to be able to find this, we need all these, I have these f of a, f prime of a, f double prime. Those all represent numbers, right? Because they represent the derivatives evaluated at a point, right? So the first thing I need is I need to find the first derivative, second, third, fourth, and right? So the idea when we're trying to find if you want to find the Taylor polynomial to a given degree, like let's say fourth degree, that means that you would need up to the fourth derivative, right? If I wanted to find up to the seventh degree, then you would need to find up to the 1, 2, 3, 4, all the way down to seventh derivative, right? So here I'm not asking for that. I'm asking for the general formula for the n. So given any degree, we're looking for the formula that will give us the Taylor polynomial for that function, which means that we find derivatives until we can see the pattern. So that's what we do, right? So once we can see what the pattern is, if we're able to predict what the terms are going to be based on the pattern, then we can say what the terms are going to be for any degree. Does that kind of make sense? The idea? So that's what we're trying to do. Whether we will succeed, I don't know. Sometimes it's difficult, sometimes it's easy, but we will see. So off we go. So I have f of x is 1 over 1 minus x. And I'm going to, it's centered at 0, right? So all of these are going to be evaluated at 0. So I'm going to do f of 0 is equal to what? 1, okay. So then I'll find the derivative. First derivative. F prime of x is equal to, what's the derivative of that? What is it? Okay, so is it a good idea to do the quotient rule? Good idea or bad idea? Bad idea, right? Because that would be complicated. The easiest thing to do is to the 1 minus x, move it up. So that means that it'll be moved up as 1 minus x to the negative 1. Then you do the chain rule, right? So you bring down the negative 1. So here, let's write it out. Just this first one, we'll write the whole thing out, and then we'll do the rest in our head. So if I bring this up, let me do here. I'll just kind of write it over here. 1 minus x. 1 minus x to the negative 1. So I bring that negative down, right? Negative 1 minus x to the negative 2, right? But then you have to use the chain rule, which means you have to multiply by the derivative of the inside, which is equal to negative 1, right? And when you combine all that together, that is actually equal to positive 1 over 1 minus x squared, right? You guys agree? Because the negatives multiply and we move the 1 minus x to the denominator, yes? Okay. All right, so that's the first derivative. So what's the first derivative at 0? 1 again. Interesting. Okay. So let's see. We'll do the second derivative. What is that? So you bring it up again, right? And then you bring the 2 down. So we're going to have a 2 over...
Wait for f prime of x.
Uh-huh.
Then we multiply by x minus a.
Well, we haven't gotten to that part yet. We will. Right now we're just finding the derivatives. And then we're going to put it together with the x minus a. Yeah, so we're not there yet. What we're doing is we're finding what these coefficients are going to be. Okay, so what is this? What's the second derivative? So I bring down the 2 and then 1 minus x cubed. Yep. And then it's going to be positive or negative? You sure? Because you bring down a negative, right? But then by the chain rule, you then multiply by another negative, so it actually turns out positive, right? So this is going to happen every time. So the second derivative at 0 is equal to 2. Okay. And we kind of start seeing the pattern, right? So we have the third derivative now is going to equal to... You bring down the 3, right? So this is going to be 6, or I want to write it as 2 times 3 over 1 minus x to the 4th. So the third derivative at 0 is equal to 2 times 3. And so at this point, you can kind of see what the pattern is, right? What's the next derivative going to be? Without finding the actual derivative, I can already tell what the next derivative is going to be, right? The fourth derivative evaluated at 0 is going to be
2 times 3 times 4.
exactly 2 times 3 and then times a 4 because I'm going to have a 4 that comes down. So at this point then, you know, you go, okay, hey, I know what the next one is. So given any derivative, so the nth derivative at 0 is equal to what? So if you know what the derivative is that you're finding, what's the number that you get? Yeah, it's just n factorial. Does that make sense? So when it's fourth derivative, it's 4 factorial. When it's third derivative, it's 3 factorial. When it's the fifth derivative, it'll be 5 factorial, and so on and so forth. Yes? Okay. So this is happy time. So whenever you can find this, then this is good news.
We don't actually need the derivative as much as the value at a of the derivative.
Right. So we need, but to find the values, yeah, we need to find. Typically, you need to find a few so that you can see the pattern. Once you can see the pattern, then you're good. So what those represent is they represent all of these coefficients, right? But after that, really, that's all you need to do, right? Because once you have those, then you can just start writing out the polynomial, and you just go up in degree. Each term has one higher degree. And what is a in my example? Yeah, a is equal to whatever I'm centered at. In this case, I'm centered at 0. So all of my x's are going to be not x minus a, but it's going to be just x. X minus 0, but you don't need to put x minus 0. It's just x raised to power. So we're going to be writing this out, but I'm going to have to move down so you won't be able to see it, but you can see it on your paper. So let's see. Okay, so that's good. All right, so then I have Tn of x is going to equal to So I have f of the value f of a, right? So f of 0, which is 1, plus f prime of 0 times what? X to the 1, right? So I'm always, each term gets, so it technically this is, let's write this out. You don't write it like this, but technically, we'll write it out this first time. This is, so f of a, it's 1 times x to the 0 over 0 factorial. That's what the first, we never write it like this because it's silly to write down x to the 0, which is 1, and 0 factorial is also the number 1. And the next one is 1 times x to the 1 over 1 factorial. And then plus the second derivative, which is 2 times what? X squared over 2 factorial. Let's do one more before we put our dots. So plus the third derivative, which is 2 times 3x cubed over 3 factorial, right? Plus, so dot, 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 plus the nth derivative, which is this one that I found, right? So n factorial x to the n over n factorial. So the n factorial from the denominator comes from the Taylor polynomial formula, right, that we derived last time. The numerators are coming from the values of the derivatives that we found. Yeah, Joe.
How is 0 factorial 1?
It's by convention. So that's what it is. Yeah. So it's just accepted because otherwise then you would have to rewrite all the formulas and it would not work out. It's just an accepted convention that 0 factorial is equal to 1. Okay, so let's simplify this. So this is, so Tn of x is equal to, this first one is just the number 1, right? Plus the second one is just x. What's the third term? It's just x squared, right? Because the 2's cancel. What about the third term? Or the fourth term, I guess. X cubed, right? Because 2 times 3 is 3 factorial. So notice all the factorials cancel, right? So plus dot 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 plus x to the n. So that's it. And if you want to write it down as a sum, let's write it down as a sum just for fun. So this is equal to the sum from k equals to 0 to n of what? I just have x's, right? Raised to power, so it would be x to the, okay. So this is the general formula. So like, for example, well, why is this useful? It's useful because let's say you are up here and, bless you. Let's say you're up here and you wanted to find T4, let's say, of x. So you would have to go through and you'd have to do the first, second, third, and then fourth derivative, right? Evaluate and all that stuff. So you would do work, stuff, right? And then you do some stuff, you go home, and then you come back and you're like, oh, okay, now I need to find the 7th Taylor polynomial. So then you go, okay, so now I need to find the first, second, third, fourth, fifth, sixth, and 7th. And then you write it out all again, right? You figure out what it all is. And let's say you come back and you're like, oh, I need to find the 5th. So then you go out and you write it all out. So once you have this formula, which you found, which is for any n. So if I want to write down, for example, T7 of x. So this is the 7th degree Taylor polynomial. And you have that formula. What does it equal? Do you have to do all the derivative stuff? No, right? You can just write it down. What would it be? Mm-mm. 1 plus x squared plus all the way up to x to the 7th, right? X to the 4th plus x to the 5th plus x to the 6th plus x to the 7th. So it's the sum of all of the terms up to that degree. So if I wanted to find T9, for example, what would it be? Yeah, 1 plus x squared plus x to the 3rd, all the way up to x to the 9th, right? Does that make sense? So this formula works for so it's, of course, just for this function. And, you know, later on in the next 2 chapters later, we'll talk more about other things that we can do with these that are great. But so any questions with that one? No? So was it easy or difficult to see the pattern? Like doing this part, because this part could be kind of a challenge, but was it relatively easy to see what that derivative is always going to end up being? Yeah, right? This wasn't too bad. So let's do one that's maybe not as obvious. Let's see. Let's go up here. So let's say we want to do, let's do another example. Let's say we want to find Tn of x for f of x equals to square root of x. And let's center it this time, centered at x equals to 1. Okay, so what's our battle plan? First thing we do is derivatives, yes, until we can see the pattern, right? And what number are we plugging into the derivatives this time? 1, right? Not 0. We're plugging in 1 because our Taylor polynomial is now centered at 1. Okay, so off we go. So f of x is root x, but let's write it as x to the 1/2 because we're going to be getting the derivative a lot. So what's f of 1? 1. Okay. So f prime of x is 1/2 x to the negative 1/2. So f prime of 1 is 1/2, right? Okay. What's the second derivative? Minus 1/4 x to the negative 3/2, right? So the second derivative at 1 is just equal to negative 1/4. Yes? Okay. The third derivative is equal to positive 3/8, right? Because we bring down the 3/2, so it's going to turn into positive 3/8 x to the negative 5/2. So the third derivative at 1 is equal to 3/8. Interesting. So what's the next one? Negative 15 over 16 x to the negative 7/2. So the fourth derivative at 1 is equal to negative 15 over 16. But let me write it like this. So let me write it as 3 times 5 over 16. So can you guys see what the next one is going to be? Can we predict? Without finding the actual derivative, can we predict the fifth, the value at 1 of the fifth derivative? What is it going to be? Positive or negative? Positive 3 times 5, and then you're going to bring down the 7, right? And then what's going to happen to the bottom? Get multiplied by 2, so it's going to turn into 32, right? Okay, so the question is this, is if you know the derivative that you're at, are you able to write down what the value of that derivative is at 1? So like if I tell you, oh, what's the 7th derivative, would you be able to tell me, or if I asked you for the 9th derivative, would you be able to tell me what it would look like? So we can kind of see the pattern, right? So what are a couple of the things that you notice? The bottom one is always 2 to a power, right? So we notice that the bottom is, so this one is 2 to the 5th, right? This one's 2 to the 4th, 2 to the 3rd. Almost. It's 2 to the n, right? So whatever derivative that is, the denominator is 2 raised to that power. Yes? Okay, so far that one's good. What else do you notice? What do you notice about the signs? Yeah, so alternating signs, right? Alternating signs, but we already know how to deal with that, right? We did one yesterday where we talked about how to express that. And then notice that this kind of looks like a factorial, but it's not really factorial, right? What is it? You're only multiplying all the odd numbers, right? So when you go to the next one, it would be, you would multiply times 9, and then the next one you would multiply by 11 and 13. Okay, so, all right, so let's start writing these things down. So if I kept going, so I'm going to do dot, dot, dot. If I want to write an expression for the nth derivative at 1, this is going to equal to, so the denominator is going to be 2 to the n, right? We already talked about that. We talked about how to deal with the alternating sign, right? You're going to have -1 raised to the n, or maybe n plus 1, depending on what you start off with, if you want it to start with positive or negative. So we have a couple of funny things going on here. One is that it doesn't quite alternate starting from the very beginning, right? Notice how it's the first 2 are positive, and then it starts alternating, right? So it only starts alternating after the second one. That's okay. We can just say that this formula that we're going to write down works for, all of the values after a certain point. But the question is, when you have the nth derivative, what is it? Is it positive or negative? So like, for example, if I have the 5th derivative right here, that one's positive, right? So would this turn out positive? -1 to the 5th? No, right? It would have to be an even power. So then what do? Yeah, just add 1, right? So that if I'm on the 5th derivative, that would add 1, making it even, so that would turn into -1 to a positive, right? If I'm, for example, on the 4th derivative, I want it to be negative. So then -1 to the 4 plus 1 is 5, right? So -1 to the 5th, that's a negative number, so that makes it negative. Does that make sense? Yeah.
Can you also just put a negative sign, multiply the equation by negative sign? If you got rid of the plus 1, it would still make
Well, that's identical, yeah, but
it's the same thing.
it is the same thing, yeah. But it's more clutter, so. But it is the same.
All right.
Doesn't it work for the very first term as well if you take anything zeros?
Well, not really, because when n is equal to 0,
Right.
that would be negative, right? Yeah. But you'll see why. So let's just kind of hold that thought. So we'll just leave that there for now, and we'll see, because we have to deal with the next one, right? We have to deal with the product of the odd numbers. So this, what you can do is we can write it as, and you can do some other fancy things, but for now, let's just write it as 1 times 3 times 5 times ... times, so in here I want an expression that gives me an odd number, of course. So this is like the end of the numbers that I am going to multiply. So if I'm on the fifth derivative, I want this number at the end to be a 7. If I'm on the fourth, I want this number to be a 5. So typically, to describe an odd number, you write it as, like, for example, 2n plus 1 or 2n minus 1, right? That's like what we did yesterday. We did 2n, I think we did plus 1, or I don't remember what we did. But, for example, if I make this 2n plus 1, would that work? In other words, if I plug in, for example, here 5, so I want to make sure that when I plug in 5 into all these n's, I get this exact same expression that I have up here. Would that work? No, why not? If I plug in 5, this would be 2 times 5 plus 1, which is 11, right? So what I would be doing is I would be multiplying 1 times 3 times 5 times 7 times 9 times 11. Yes? Okay, so that doesn't work. So how can I change this? So how can I change this so that this ends at the right spot? 2n minus 1? Would that work? 2n minus 3, yeah. So if I change this to 2n minus 3, that works, right? Because if I plug in 5, what does that equal to? 7. So that means I would multiply 1 times 3 times 5 times 7. If I plug in 4, that would be 2 times 4 minus 3, which is...
Does it matter that it's not in the first one?
Well, yeah. So it doesn't really matter. So where does it start working? Does it work for the so let's go back a little bit. If I plug in 2, does this expression work? So it does, right? Because if I plug in 2, this would be 2 times 2 is 4 minus 3 is 1, right? 1 over 2 squared. So 1 over 2 squared, and then 2 plus 1 is 3, so it comes out negative, right? So that thumbs up, it works for the second derivative. But what about 1? For 1, it doesn't work, right? Because 2 minus 3 is, if I plug in 1, oh, that's not a good color. If I plug in n equals to 1, I would get negative 1 squared times, if you plug in 1 here, you get negative 1, right? Over 2. Does that equal to positive 1/2? No, right? So then we'll just add a little note here that this is for n greater than or equal to 2. And that's it. So we can do other things, but I think at this point it would just add some unnecessary confusion. But this is enough because this gives us an expression that works for all the derivatives. As long as we're past the second derivative, then we're good to go. So what we can do is we can write it out. With it, this is enough information for us to be able to write it out. Because we can go, okay, so let's see. Tn of x is equal to, so everything else is going to be the same. So f of a, which is 1, right? Hello. Respond. Okay. 1 plus, what's my next coefficient? 1/2. Right? Where did that 1/2 come from? Well, it's this one, right? 1/2 x what? This time it's centered at 1, right? So this time it's going to be x minus 1 raised to the 1 over 1 factorial. Okay, now what's the next term? What's the coefficient? negative 1/4 times x minus 1 to the squared over 2 factorial. Yep. Okay. What's the next term? Plus 3/8 x minus 1 to the third power over 3 factorial. Okay, and then, so at this point we can just put in our general form. So let's see if we can fit it on here. So what I'm going to do next is just write down what the general expression is. Since that expression is valid for as long as n is greater than 2, so I'm past 2, right? I already passed 3, so I can just write negative 1 to the n plus 1 times, just for space, I'm going to leave out the 1. Is that okay? So 3 times 5 times ... 2n minus 3 over 2 to the n times x minus 1 to the n over n factorial. And so that's the general Taylor polynomial for square root of x centered at 1. Yes, go ahead.
I don't get how that expression gives you the after the 1 times 3 times 5 ...
Yes.
I don't know where that, I could see that for one term, but what about the next one? How does it account for all of them multiplying by each other?
Well, because you're writing this out, when you write this out, so what you're saying is this is the product starting at 1, and you're saying going in that same pattern. So 1 times 3 times 5. So that describes that you're multiplying the odd numbers. And this 2n minus 3 just describes what the last factor is going to be. So if, for example, let's just say hypothetically you wanted to find the 9th derivative at 1. So this would be negative 1 to the 9 plus 1 is 10. And then you would multiply times 1 times 3 times 5 times 7 times 9. So you would do this, and when do you stop? Well, this is what tells you when to stop. It tells you to stop when 2 times, in this case, 9 minus 3, whenever you reach, what is that number? 15, that's when you stop. So that means you're going to go in the same pattern until you get to 15, and that's when you stop.
But isn't that vague? Can't some other pattern?
It is vague. I mean, it's a little vague. It's not really vague. You can... So sometimes you can't write it in closed form. In this case, we can, but I feel like it would confuse more than help, and I think this is, at this point, better to leave it like this. Because if we get into how to create these things using factorials, I think it would make it more confusing at this stage. The beginning stage, because we're going to see these a lot. So, if it's if you're not 100% satisfied with this, then that is okay. But what you can do, and this is a great idea, is if you go on. Okay, so do this. If you're still not comfortable and you would like more fun. Go on Wikipedia, Wiki Fun. No, not Wiki Fun. All right. Anyways, whatever. And type in double factorial. And you can see how to create, how to write this in closed form using factorials It just involves writing this a little bit differently, and you can write it. It's just I don't really want to get into it right because I think it would confuse more than help. So, does that make sense? Do you guys have any questions?